Hello, my name is Zihan Yang. My talk is about the conductive and elastic 3D helical fibers that can be used in washable and wearable electronics. The three keywords are conductive, elastic fibers, and washable. This is a collaborative work between the Professor Hanqingjian's group at Arizona State University and the Professor Yingzhu Wu group at Wuyi University. Wearable and flexible electronics has been significantly advanced by many groups. Two exemplar experts are Professor John Roger and Yonggang Huang at Northwestern University. They use soft materials such as PDNS as the substrate and the mechanical instability to make wearable electronics. Great achievement has been achieved as highlighted by their high-profile publications. However, soft material-based wearable electronics have some limitations. They are often uncomfortable and not durable, such as limited stretchability, not enough soft, and not breathable. More importantly, they are not washable. Washability should be an important factor to consider for wearable electronics. So, what is really washable? Clothes. They are breathable and washable. There are some efforts to make fabric-based wearable electronics. Here are some examples of fiber-based wearable electronics. This work uses silver nanoparticle called Kevlar fibers, and this work uses conductive polymer-based fibers. For this one, they have low stretchability, and for this one, they have low conductivity and solderability. Solderability is an important property to ensure the fiber can be electrically connected with other components. For these two work, liquid metal filled fibers have low solderability. The carbon nanotube-based fibers are not solderable. To sum up, fiber-based wearable electronics have the following major limitations that limit the use in clothing: low stretchability, low conductivity, low washability, and low solderability. So, our motivation is to develop fabric-based, highly structured, conductive, washable, and solderable interconnects. Inspired by the buccal silicon supported by soft substrate using the mechanical instability, we use the polyurethane as the elastic material and the copper fiber as the conductive material to prepare the fiber-based wearable electronics. First, the PU fiber was pre-stretched by a large strength ranging from 100% to 400%. Then they were coated with cyanoacrylate and bound with copper fiber with radius about 30 micrometers. The contraction of the pre-stressed PU fiber buckles and twists to form a 3D helical shape. In this fiber, the higher conductivity and solderability is provided by the copper wires, whereas the stretchability is provided by the 3D helical shape of the fiber. Furthermore, a waterproof coating on the outside of the 3D helical fibers enables washability. Here is the device designed to make the helix-shaped fibers. The pre-stress is controlled by controlling the speed difference of the drum. After releasing the tension at both ends, the composite fibers retracted to form the spiral structure. This figure shows a buccal helical fiber with 400% polystrate. Figure B to E shows its SEM image, and the closed section of the composite fiber is shown in Figure D, in which the cyclohexyl layer forms a uniform coating to provide a robust barrier for the composite fiber. This is in line with our expectation. We also conduct finite element analysis to understand the mechanism. In this structure, the practice material is a carpeting alloy, and the elastic material is insulating polymer and polyurethane. Due to the helix morphology, the length of the fiber retracted from 100 mm to 14.6 mm. It is greater than 400% polystrate. And then we can see that the middle section of helical fiber can produce periodic helix. The diameter of helix D decreased from approximately 1.4 mm to 0.6 mm as the polystrate increased from 100% to 400%. The experiment results agree very well with the simulation, and the simulated 3D helical shape are shown on the right. A 3D helix is described by two parameters, diameter d and the helical angle alpha. The pitch of the 3D helix lambda is related to these two parameters via this formula. The diameter of the PU fiber is 80 micrometers, whereas that of the copper fibers range from 25 to 40 micrometers. Through finite element analysis, the helix diameter decreases as polystrate increases for the different copper and PU fiber diameters. Under the same polystrate, thicker copper fibers lead to larger helix diameters. In contrast, the helix angle increases slightly as polystrate increases. The behavior is intuitive because thicker copper fibers have higher bending stiffness. Because of the helical structure, the fiber is stretchable. We can see that it fully recovers after 80% straight. It can be structured to 400% without breaking. As verified in these pictures, which shows the straight relationship of the helical fibers using different polystrates. Since the helical angle increases with increasing polystrate, the limiting straight decreases as the polystrate increases. The helical fibers are extremely soft before reaching the limiting straight and become much stiffer thereafter because of the direct stress of the copper fibers. The equivalent stiffness before reaching the limit straight is approximately 1 megapascal, which is on the same order of magnitude as the stiffness of the skin. The strength of the composite fibers come from two parts, the PU and the copper fibers. PU fibers with larger polystrates offer greater contributions. Thus, the strength of the PU fibers is greater at higher polystrate. The electrical performance was tested as shown on the left. negligible variation is observed, and the maximum change is approximately 0.07% at 200% deformable straight. In the picture at right, change of electrical resistance when the 3D helical fiber is straight at 35% straight for 500 cycles. The maximum resistance changing is less than 0.03%. Here we compare the performance of the present work with some reported results. We find that it is apparent that the present works outperform all the reported results in terms of both the conductivity and the relative variation in electrical resistance. Specifically, the conductivity of fibers in the present work is several orders of magnitude higher than that in many of the existing studies, and is roughly on the same order of magnitude as the conductivity of the in-touch carbon fibers. Now, we test the washable property of the fibers. Ultrasonic washing, which is a much more powerful washing approach than household laundry washing, was used to remove solid particles from the object's surface. As shown, the fibers are washed for 100 minutes at 20 degrees Celsius. The fiber does not show severe mechanical damage, and the morphology remained unchanged. The image on the left presents the small variation in the mechanical strength of the 3D helical fiber at different washing times. On the right, the negligible variations in the relative electrical resistance trends at different times during washing. These results show its stable mechanical and electrical performance. Now, we test the usefulness of the fiber in electric products. The fibers were sold to a flexible printed circuit board using a standard soldering process. The cyanoacrylate and the PU fiber were melted at 200 degrees Celsius, and the copper fiber were exposed to form a joint with the flexible printed circuit board. Moreover, a mechanical test was conducted, and the results showed that the solder joint has strong mechanical integrity, and that the fracture occurs at the fiber, not at the joint. Compared with other solutions to joint conductive fibers, such as using silver paste, the present method is mechanically robust and electrically efficient. Here we soldered the fiber to the LED and did a stress test. This video shows that the solder piece is very robust to deformation. It is worth mentioning that since the copper fiber is continuous, the soldering point can be found at any location in the 3D helical fibers. This is helpful for designing wearable electronics. The present fiber can be woven into fabric using both weaving and knitting. SEM image shows that the 3D helical fiber can be nicely integrated into a fabric, particularly for knitted fabric. The thickness of fabric is about 1 mm, and the 3D shape of the helical fiber is non-tactile. To demonstrate an integrated device with the present 3D helical fibers and other functional components. A wristband which consists of a battery, LEDs, and the 3D helical fibers as the internet was made. The fibers perfectly fit in the textile and cannot be distinguished. This video shows the functioning wristband upon 35% strain. Because of the protection of the waterproof coating, the wristband still functions when immersed in the water. Even after exhibiting clamping, the wristband still functions. A quick summary here. We report a way to make highly structurable, conductive, washable, and solderable fibers consisting an elastic PU fiber and conductive copper fibers. The developed fibers can be used as interconnect for wearable electronics. It can be seamlessly integrated with clothes by virtue of its 3D helical structure. This work may provide a new direction for wearable electronics. In the future, the strategy of producing 3D helical fibers can be used to design devices with other functions, such as stretchable heaters, circuits, and optical fibers. We will be available to discover with you via this Zoom link. Thank you for watching.